TTL Computer 2. Today, we're going to be taking a look at our registers, card, schematic, and PCB design. And we'll just get right to this. Okay, so we're looking at the first sheet in our registers, card, schematic. And this is virtually identical to our digital simulation. The only thing that's significantly different is the addition of the 33 ohm resistor networks that we use as a for impedance matching to our bus from our bus drivers. So that's been added. The only other change I think that I made was that I reordered these signals, and they were D0 to D7. I switched those around again to eliminate unnecessary crossovers, lines crossing over in the PCB design. So those are the only changes I made. Other than that, this is almost virtually identical to our digital design. And then our second sheet are for our passive elements. We have our bypass capacitors for each of our ICs. We have 3 power decoupling capacitors that we're going to use on the board. And we have our power indicator again. And then we have our card edge connector. So again, these are the standard positions for our clock signals and our clear. It's a clear, not clock, P clock, U clock, and T clock. This card only uses the U and the T clock. This will be the area for the rest of our control signals. And right, A in, A out and A in, B out and B in, C out and C in, X out and X in, and stack out and stack in. Those are our control signals to the card. Then we have our right bus output byte. We have our left bus output byte, and we have our data bus as input to the card, and power and ground. So this is pretty similar to the other cards. Okay, so those are our 2 schematics, and then on to our registers card design. Okay. All right, so you can see that this is a pretty densely populated card. The card size is the same as we've used on our last few cards, 200 by 150 millimeters. So again, I'm going to try and standardize on that. So the only card that's smaller than that is the clock card. So you can see we kind of have some of the same layout elements. We have our input 245 buffers to the left, and then we have our output bus drivers to the right with our 33 ohm resistors, and the input signals are coming in here. We have some coming in on the bottom, right? So let's take a look at the bottom routing. So this is our data bus. Comes in is routed on the bottom, up and around to the top, so that those signals will all be pulled down to the registers from above. Okay, and then we have some of our input lines are routed on the top. We have these 2. These are control. The control signals come through here. They're routed from the top off of the card edge, but right then they are pulled up and around as the data bus lines were. And so to look at the rest of our major routing on the bottom. So our inputs come up above and they're pulled down to our register ICs. Then the outputs, we have 4 of these registers output on the the left bus, I think it is. I don't remember. The left or the right bus. 4 of them are the same, and these are all, directly wired together to form the bus line and then brought down to the output. It's just the single, the one register that is the X register that's output on the right bus, I think it is. I'm not sure. I don't remember. And that's pulled down here and then out to the card edge on the bottom. Okay. And then on our top right, we are mainly used to pull down our bus lines to our ICs. Same thing here. We pull in the required signals from the bus and control lines to our logic ICs. These are NAND gates, I think, and this is just another AND gates, I believe, that are just doing combinational logic that we need to primarily drive the clock signals to each of the chips for their clock in signal and one output enable signal that's required here. So this was this was the most complicated card design that I did. It took me quite a while to do the routing here. And again, this is all manual routing is what I'm doing at this point. And the routing pretty much went pretty much as expected. I started out with the input routing and bringing that around. Then I did the output routing from the registers down to here, and that left this combinatorial logic in the middle. And I was getting a little worried that I wasn't going to be able to do that. In other words, painting myself into a corner, but it came out okay. And only 2 signals, I think, I had to change planes to be able to route the signals. One of them was here. You can see that the bottom, this is routed on the bottom. Then we have a via, and I had to go over these other lines. Same thing here. I had to have, the trace start on the top, and then a via, and then go transition to the bottom layer. So those were the only two places where I had to jump layers with the via, by a via. So I didn't do too badly. Went pretty much according to plan. Okay. So that's what our routing looks like. And then we can take a look at our 3D model. Okay. And much as we've seen before. So this, again, looks pretty good. Key thing to look at also, right, is just be concerned with that there's just a little gap at the bottom between the connector and the board. Just a little gap, and I want to keep that there. I don't want the tolerance to be too tight. So that looks good. So we just take a look at the bottom of the board. Right, the bottom of our board and the top of our board. Okay, so that is pretty much complete at this point. I have to just do a little bit of silk screen work to add my logo of sorts to the board and just do a final checkout, and then this will be off to fabrication in about a day. Okay, so that is our registers card. I think I'm looking forward to actually testing this out in our jig, because there's a lot of interesting behavior that we need to test and will be a good fit for our testing jig. So I'm anxious to do that, and that'll be I think fun to watch too. Okay, so that's it for today. Until next time, thanks for watching.